invite me. I insist to be invited, in a sense that I really want to be here and enjoy. And I had a big ambition to give a talk which will be explicit to us, very simple, and maybe of wide interest. Maybe the most explicit, but I'm afraid I failed today after the talk of Younger, because this talk was brilliant and it's difficult to compete. Anyway, what I want to share with you some non-orthodox view and non-orthodox definition of quantization. And you will see how it works. But I will begin with a very simple thing. So don't be scared. I will not talk all about all this. I will talk about the first part is kind of introduction and the definition, which I will use. Second part is example which I want to cover during my lecture. Third part, I will see how I proceed. And the last two parts, probably, if questions will be questions, I will just choose some slides from this part to answer questions. So basically, what I want to do, I want to give a little bit non-orthodox definition of quantization. And let's begin from the orthodox definition. Simple thing is classical mechanics and quantum, and I choose most simple example one can imagine. So we have Newton equation, and instead of phase, I like to talk about space of functions of space. But this object is better to generalize the quantum case. And in my case, it will be sufficient to consider polynomials of two variables, P and Q, and these variables commute. We have Newton equation, with a second derivative of Q is force, which is we have first integral. First integral is constant time. We can equip this with Poisson bracket between T and Q equal to 1. And well, I will not define Poisson brackets so much. And then the equation can be written in Hamilton form, and any variable which depend on T and Q can be differentiated in time, just taking Poisson brackets with H, which is H is the first integral. Quantum mechanics, we dealing with non-commutative objects. So basically, we can consider, for instance, some free algebra with variables P and Q, and with the ideal generated by this commutation relation. Or just you can see there is a commutation relation, and everything organized with this commutation relation. And what was observation of and discovery in quantum mechanics that of Heisenberg, that equation of motion does not change. They change the rule how we work with variables. Variables not commute anymore. They satisfy the commutation relation, the Heisenberg commutation relation, and the first integral, which used to be first, is still first integral. So if you differentiate H and use just Leibniz rule with linearity, you will and the rule of commutation, you will see that is 0. And instead of Heisenberg Hamilton equation, you have Heisenberg equation. So that is your equation of motion can be written in this form, and any function of your P and Q, which are polynomials in two non-commutative variables, can be differentiated using just taking commutator with Hamiltonian. And what Dirac noticed, and that was the story in 1925, that in the continuous limit, the commutator goes to IH multiplied by Poisson bracket. So in a sense, that moment, the idea of information quantization was born. So to replace commutative elements by non-commutative, such that in the limit we get IH multiplied by Poisson bracket that may give higher corrections in H. And there is a big progress in this theory, you know, fields, medals, etc., how to deform Poisson manifolds. But there are still lots of questions. And these questions actually originate to original paper of Dirac 95. No, first question is, of course, you do this and you have to be sure that the multiplication is still associated. Secondly, consistency is if anything is good, if h goes to 0 and the leading term is Poisson bracket, and we know that classical mechanics is consistent, then in the paper of Dirac, there is a question: is it consistent for finite h? That is the issue which needs to be addressed. Another issue which has not been even resolved up to now, and is ordering of operators. If we have the classical case, we have PQ, we can write any polynomial, don't care about the order. In quantum case, the answer will depend on the order. So what ordering we have to choose? And there is no any canonical way to do it. And there are two other issues I want to discuss today. Is in the first lecture, today, the first talk, later we talk about some multi-Hamiltonian structures, right? And how these multi-Hamiltonian structures can be recast in the quantum on the quantum level. And the last question: how can identify non-deformation quantization? Because deformation is clear. You have for some structure, you just take some deformation of algebra multiplication, which has this property. And what means non-deformation? How to define this object? So that's what I'm trying to kind of give partial answer and maybe set more questions, proposing a different approach to quantization, different definition. And what I want to start with, not a commutative case, as everybody starts with Hamiltonian structure, etc. But I want to start from equations defined on pre-associative algebra. We just have pre-associative algebra. But let's, in this case, it will be more in this particular simple example. We have two variables p and q. We can write any polynomials in any order. Take sums with the complex coefficients. It's a pre. We just don't know how to solve this with variables. How to all words written in this alphabet are different. That is a pre-algebra. We can write Newton equation or whatever this equation in this term. So if polynomial equations are well defined here, if you don't like pre-algebra, you can think that P and Q are matrices, but the dimension not fixed, because if it's fixed, it's not free. So any big size matrix. Maybe these equations and equations on pre-algebra have certain sense which I don't know. I use it as a way to define quantum theory, but they may have some sense because people study, for instance, random matrices, etc. So they may have some probabilistic sense, maybe. I don't know. But now I use these things as an intermediate step to define what I want to do, what I mean by quantization. But before that, let's say a few words about the properties of these equations. First of all, whether we have first integrals. And the answer, yes, we do have first integrals. For instance, H0, which is commutator of P and Q, if you differentiate, use the Leibniz rule of linearity, you will see it's 0. So there is first. But if you take the Hamiltonian, the former Hamiltonian or former first integral, and if U is not quadratic in Q, then the result is not give you not with 0, but give you some polynomial. This polynomial lives in the span of commutator of pre-algebra itself. It's not ideal, it's a linear space. And people usually define that, okay, by first integrals we will call the quotient space of our algebra over span, or simply something if you say about matrices, we take the trace. The trace. If you have trace, all commutators go, right? Because under trace you have small cyclic terms. So, and that we can define these integrals. And if in Newton equation we have only one first integral with Hamiltonian, every algebra integral is just a polynomial of that. On free algebra, we have infinitely many algebraically independent polynomials. And infinitely many, we will have in this equation have infinitely many cases. About symmetries, well, by symmetries, there are plenty of definitions. One we can consider, for my purposes, enough to consider derivations which commute with the derivation given by our equation. So that is a symmetry. It's infinitesimal symmetry, algebra infinitesimal symmetries, and there are infinitely many. This equation has infinitely many symmetries. In the commutative case, you don't have any. So that is but in commutative case, that gives you 0, and that gives you the equation itself multiplied by cos theta. So not nothing. So there are some problems. Now, what's the main difference between free algebra and which I try to work with, and the commutative and quantum case in the standard approach? That free algebra grow very fast because every word in let us P and Q will be different, and if you fix the power, the number of independent monomials grows like 2 power n, or number of letters and number of power n, easy to compute. But in the commutative case, and commutative case also can be seen as a quotient of free algebra over ideals generated by the commutant, or in quantum case, where quantum algebra is a quotient of free over these two-sided ideals generated by this relation or commutation relation, we can always swap variables and put, for instance, P in front and Q behind. And the number of monomials grows like n plus 1. So we want to have something quantum very close to classical. So that property we want to change and keep. And physicists usually use so-called normal ordering. They select some ordering. There are plenty of orderings. For instance, they always can put P in front of Q, and they use it's just identity modular of our idea. Just identity. And if you use this identity, you can immediately see that, for instance, here Hamiltonian was not 0, but if you put P in front and P in front here, use these identities, you will have 0. That's how it works. So in quantum case, it is just it. Now my main slide, where I give definition, non-orthodox definition of quantization. So first, I start from the mathematical part. So what we do, we want to build a system not commutative but of some algebra. But any algebra can be realized or is isomorphic to a quotient. I mean, associative algebra is a quotient of a free algebra or a suitable two-sided idea, right? Or the suitable two-sided idea. Now the problem focus on ideals. What I want from these ideals, because I want to consider quotient, I need some properties of ideals. And the main property of ideal, that ideals should be stable with respect to dynamics. So we don't quantize Poisson manifolds. We don't quantize anything like that. We forget about all Hamilton stuff and all Poisson stuff. We look on dynamical system, which is given to us. We may not know even the Hamiltonian structure at all. We don't use. But the dynamical system defines for us the derivation of the algebra. What we want that our ideal state. So if we differentiate ideal, any element of ideal with respect to our dynamics, we are still there. So if your commutation relation that times 0 satisfied for every moment of time, simply speaking. So that is one property, and this property is absolutely essential to reduce our system. Okay, that is terminology. I understand that you understand. I mean invariant. Our ideal is invariant with respect to derivation given by dynamical system. And that it works not only with finite dimensions, we work with infinite dimensions as well, very, very well. So our ideals should be invariant with respect to our integration. That is first. And second, I just want to kind of mimic or implement this property that we can swap it into variables. That means that in the function algebra we can swap all cosets and make this normal logic, implement normal logic. So that's what I want to do. So I have that is additional thing which is we can discuss because I have something how we will come to this little later. And if ideal satisfy these two conditions, I call this ideal quantization ideal, and that will be quantum algebra. And so that basically what I mean by quantization is a reduction of a system given on a free associative algebra to algebra with this on the function algebra with this special property where we can swap and equate. Looks a little bit too general, but of course it will cover all existing ways of quantization of what we know. Give a little bit more, but not much more. Surprisingly, right? Of course, there is a very delicate question about ordering because we can if we want to start from if you want to start from commutative case, first you want to lead it to reality. Of course, you can write it as if there are things in a way. You can always set element from. And but what the guiding principle here, as I understand, is the following. When we have a system which we want on quantize or work with, we have some properties which we cherish. And what we cherish? We usually cherish some symmetries or some, if it is integrable, there are hierarchical symmetries. If it is some relativistic or whatever, we have some symmetries that we want to keep. And that is a kind of guidance, so it reduces the possibilities in which we can lift the system to reality. And that's for a moment again about the system to work with system of reality. No, first of all, what kind of ideas? I don't know general theory in this case. I cannot make a general statement, but there is a very good type of ideals which works and satisfies all the properties. And this type of ideals is the following. So, in general, the algebra, the identity biases any words of our variables. So we have, for instance, 10 variables, we write any words in any powers, that they are all different. Now I want any two letters to swap. When I swap these letters, I don't want to have some nilpotency. Well, that can be discussed, but at the moment I don't want to discuss it. We just swap and multiply by some constant. We don't know this constant. We just is a parameter in our theory, and plus some extra polynomial. In order things to work, we need that there is some ordering, lexicographic ordering in our variables and lexicographic ordering in monomials to keep this ordering. And if we have this ordering in such a way that that is a highest term, that is term a bit lower, and the leading monomial of G is lower than that one, then the procedure goes and we do it very actually. We can develop it as we have well-defined ideal which enable us to swap any two letters, and in this case our algebra will have this normally ordered basis or comparative of equations, and there is a training mathematician Lewandowski who works in Kaiserslautern, his thesis was about this kind of ideals and this kind of algebras that was studied by quite well. Now, I don't usually I go to some simple examples to Newton equation, but now I want to show you a little bit more scientific example, which you probably know and very well studied, and want to show how this thing works. Let's consider the tautologies, either periodic tautologies or on an infinite line. Don't worry about infinite line. We have to algebra with infinite number of letters, but every element in algebra is a finite polynomial, finite number of letters. Everything is correct. Now let's look. The tautologies is known to be multiple Hamiltonian system. Actually, it is known to be three Hamiltonian systems. There are three Hamiltonian, three Poisson brackets. I write only two because I don't know how to work with the third one. So we have tautologies. Usually people introduce these variables. I think after Flashka introduced A and B variables. The classical tautologies was integrated by Flashka and Manakov independently long ago. Let's pair all the stuff. Was the presentation of Manakov actually, and I remember that time. So we have then this system of will be written in the polynomial. It's polynomial equation. So we can consider algebra generated by letters A and B. And here are if it is commutative case, don't you can put variables in any order. And in commutative case, we have two Hamiltonian structures. One Hamiltonian structure given by these Poisson brackets, and the rest Poisson brackets that's here. And H1 here, H1 is so commutative. And there is a second Poisson bracket here, which given by these identities, and all other Poisson brackets are zero. These Poisson brackets are compatible, so there is a Poisson pencil, as we talked during the first lecture today, the first talk today. So that is a multi-Hamiltonian, bi-Hamiltonian structure of the classical tautologies. Now we want to move to the quantum tautologies. In order to move, first I move to, there are infinitely many integrals of motions which are written here, H1, H2. If some is finite, no questions at all. They are just normal proceedings. And of course, fine. Okay. And there is a way from if a system is, now we can leave this system on a free algebra. And on a free algebra, look, I have bk plus 1 in front and bk behind here. And that is the only ordering I have to care about. And actually, that follows somehow from Black's pair, and you can show that this system will have infinitely many, the whole hierarchy of symmetries, everything to wide. So that is a correct way to leave the system to non-commutative. So in this equation, you can see that A and B not commutative, just elements of real. And of course, K goes from 0 to n, for instance, if it's finite, or infinity if it's infinite. So that is our tautologies on the free algebra. So that is the tautologies. I need to write only one equation because everything is shifted variant. So that is usually people have write this equation. Now we can ask about these ideals, which I showed you ideals before, and ask the question whether we can write ideal, find constant, such constant of this ideal, because we have many constants which define our polynomials, and such that the ideal is invariant. And answer is very simple. So indeed, the ideal exists. Moreover, there exists ideal which depends on two parameters. So you can fix these two parameters if you fit h and theta. If you set h equals 0 and theta equal 1, that will be just commutant because everything complete. If you take then you can, well, basically, probably people would call it algebra. You have two parameters, theta and h, and every point theta and h plane, you have ideal, you can consider function, you have algebra at every point h and theta. That's what structure. Now, then you can use this ideal, or you can consider that as commutation relation for your system, like just commutation relation. So elements D and A commute if they far from each other, and if they are close to each other, they commute according to these rules. Then you can check that these guys are exactly first integrals to the quantum system. And if h is 0 and theta is 0, then they should be classical and they can cite this classical. So we have a very similar thing. So I just want to show you that there is a similarity between the classical and quantum. Then this idea. Maybe I will do it on the next example, okay? Because it's easy to explain. I have another example I will show you. But I want to just highlight the similarity. In classical case, in Hamiltonian case, we have Poisson bracket 1. In quantum case, if we set h to 0 and theta is not 0, we have the commutations. But look, it's exactly what Dirac told us. It's a information quantization, right? We just have information quantization. Now we can set theta to 0 and h keep as a parameter. So then we will have another set of Poisson brackets. The rest is 0, and we have the corresponding ideal or commutation relations due to the ideal here. And look, it's exactly another information. So we have basically we have Poisson pencil and we have Poisson structure depending on two parameters, and we can deform it and get a quantum system with two Planck constants. And H1 was Casimir, and H1 will be the central element of algebra with respect to the first quantization. And the equation of motion can be written with H2. Look, if you take the H1, it's not Casimir, you will get equation of motion that they well, it's anything differentiation or equation of motion. So dt is a commutator with H1 with the first quantization, with the second quantization, or dt is commutator with H2 with second, etc. So that is exactly the picture you can get, and you have infinitely many conservation laws, you have quantum symmetries, everything works. But not yet. It works here, but we also know that we also know that there are other total lines. Because what total lines I can see here is correspond to AC, A1. And there are total lines related to other affine algebras, AF2, ABCT, all the possible. What happens with that? And the simplest example is a so-called Cetec equation, which corresponds to A2. Total lines corresponds to A2. And here is the first abstraction. You cannot, at the moment, I don't know, and there is no simple way, probably no way at all, to lift this equation to pre-algebra, keeping the whole hierarchy of C. Because when you create these algebras, affine algebras, you use transposition. And transposition in the algebra, you have equation and transpose equation. And you remove the case inside. And here we go. So we have this problem, need to work on it, but this is still so, and that means, I believe, and I searched on the internet, that when people try to quantize standard code of sine bond, they have no problem. Everything with each other, we have consistent picture. When you go try to consider systems they talk about anomalies, etc. So that it's not so okay. I think the root of that, because it's difficult to reach this system reality. Maybe there is another way to do it. How much time? Right. Now I want to talk about non-deformation quantification, because when I define my stuff, I didn't say a word about Hamiltonian structure, about Poisson brackets, about things like that. So they don't play a role. Let's consider not totalizing, but the next equation in the hierarchy of totalizing. Totalizing doesn't have this thing. But next term in hierarchy, which compute with totalizing, and there are infinitely many these terms, so-called even terms, when you have, well, basically we have in Hamiltonian correspond to even b squared, d even power. Well, there is a kind of defined even sub-hierarchy. So you have hierarchy which is all natural numbers, but there is an even sub-hierarchy which is very even. And the first equation in this hierarchy is here. I can write it by this equation. And you ask the same question about the, and you find surprisingly two answers. One answer is, of course, the answer you had before. And that will be true for the whole hierarchy. But there is another answer which does not exist for total hierarchy, but it exists for even. And this answer is here. That is a commutation relation. Look, if some elements not commute, some not commute with whatever h you take, you cannot move to either to Grassmann. Okay, in Grassmann case, you can say that you have the formation of Grassmann algebra. Grassmann algebra, there is for some structure, everything will be okay. You can consider it. But it is not. It is new algebra, absolutely new algebra. This algebra is consistent with dynamics. This algebra is consistent with dynamics. This algebra enables us to swap any two elements. So that is a, I mean, in my definition, non-orthodox definition, it's legitimate quantization. But it has no any limit if h goes to 0 to any commutative or anti-commutative algebra you know. But this type, you know. But if you want to write equation of motion, you use the same h as before, but new commutation rules, and you will get exactly the same Heisenberg equation. Look, we don't have Poisson equation, we don't have Hamiltonian equation, we don't have Poisson brackets, but we still have Heisenberg equation with a new, and that I would call non-deformation quantization, because we don't deform the Poisson bracket, we just find a proper, ideal. When I did talk recently, I think Rishtikin asked me, I'm sure that there is no any Poisson brackets, which would fit this thing. I don't know the answer, because maybe you can redefine Poisson brackets, like people redefine Poisson brackets to rational. They get something, some great, etc., everything stuff you want. Now I will probably you heard about Quantera system, but they are also related to Toda by neural transformation. But Quantera was the first, and maybe I will answer your question how I did. So Quantera system was originally created by Manakov, and later was known as Kastan-Norbitten. And there are long story about it. But in the free algebra, I think Quantera was mostly mentioned by probably Mikhailov, that was also paper for get fun. Yeah, but I think probably will be difficult. Mikhailov, right? Big review paper. I don't exist. Okay. Anyway, so let's consider first a very simple idea. Infinitely many constants. When we swap two elements, we swap only a bigger than 2. We multiply by a constant which is a non-zero. That is the commutation relation. This ideal already satisfies our property we can order it. But then what we do, we differentiate this ideal with respect to this equation and request that modulo this ideal be again so we again get to the and that gives you simple equations, polynomial algebraic equations on this constant omega. And we start from infinitely many constant omega, and we end up with a very simple commutation relation. This commutation relation, of course, was known, and for instance, the Nomi, this Japanese lady, use many people use it, but they use quantum spectral transform method, Faddeev construction, etc. And that is a 3 lines computation. You get all this commutation relation and nothing else. And you can write in your equation that your commutation relation, that the far points commute, the closest point commute of why I put exponential IH, because I want to add some physics that I say that there is admission, then it should be 1, and then you can write your Valtteri equation in this form, in the Heisenberg form. That is your Planck constant, that is your Hamiltonian, there are many. So that's how things works. And we proved with Sylvain Carpentier and Jim Van that this quantization, I would say, or this ideal is invariant not only with respect to Valtteri, but the whole hierarchy of Valtteri equation. This proof is unfortunately was done by brute force. It's not very intelligent proof, it's just brute force, but some combinatorial. But it is proven, and you can find the second term of this quantization here, for instance, second equation, and that is second Hamiltonian. And then we can set another question about non-deformation quantization. So if you take a second term of the hierarchy, this one, then there are 2 answers. One is like Valtteri, and another is, well, that is probably easier to see, that it is not anti-commutative. This term is anti-commutative. Therefore, alpha you take plus or minus, it will be never plus minus. That is non-deformation. But you still have the same, exactly the same Heisenberg equation for this quantization. Now, doing this, and we also prove it for all the hierarchy, for all even hierarchy. It's not just one, it's all even hierarchy has its proof. So all even hierarchy has its second quantization. Here I give some example of the ideal which is not satisfying the condition that we can swap any 2 elements. But this ideal is invariant with respect to Valtteri. And quotient of algebra, so equation will be well defined on this algebra. The only luck that the algebra will grow a little bit faster than the commutative algebra. Probably that what another example may be useful. Why we use such a poor simple ideal for quantization? If we consider periodic chain, and periodic chain, well, we just can say that UKN plus n equal to UK, or take quotient over this ratio, then you can reduce your hierarchy of total lattice and all symmetries to finite dimensional dynamical C2C equations and C symmetries, etc. Right? And then if you have finite number of equations, you can afford to study more general ideals like quadratic, linear term, constant term, this. And then this ideal automatically satisfies that everything can be swapped and normally ordered. But if you try to differentiate this ideal with respect to Valtteri dynamics, you will discover that there are following picture. If m equals 3, that the ideal generated by these 3 polynomials. So alpha, beta, and eta, only 3 constants survive. If m equals 4, also 3 constants survive, but in a very different way. So you example, you have constant only 3, but you know it's a very peculiar way. But we cannot do anything because that is a result of algebraic solution of algebraic equations. It's not just our guess. And if m equals 5 or more, then there is no any extra constants allowed. Sigma or eta not allowed. You will have only the quantization when you swap u and u and multiply by a constant. That's it. Nothing else. That is answer. Here is example with n equals 3, maybe not interesting. Well, interesting in the sense that here we already first time can see bi-Hamiltonian structure for total lattice with three elements, because we have two parameters, nu and nu, and the bi-Hamiltonian structure of this equation in commutative case with respect to two different Poisson brackets. We have two first integrals, and that is a Poisson pencil basically. And in a quantum case, you have exactly the same picture. Yeah, I know. I know. So Volterra system, that is a first example of finite Volterra system with a non-deformation quantization, where it can be easily seen, all the commutators. And that is super integrable system because we have 4 equations of first order, we have 3 first integrals, or three first integrals, or we can have three central elements of the algebra, and the equation can be written in the form of the Heisenberg form. So same works for KdV equation, for stationary KdV equation. The same picture works for stationary KdV equation, etc., etc. So it works. That's what I want to say. But more questions remains. One question which bothered me a lot: how to deal with, for instance, this affine daughters. Another thing that works not only differential difference equation, the same idea applies to maps. Because what we will need that your ideal is invariant with respect to maps. And then you can reduce the quotient over the ideal, and you can quantize the maps. So that is a kind of beginning of something. I don't know if you guys have seen that before, etc. I spoke to people and I will love suggestions.
So I understand that the first issue is finding a systematic way of finding decided idea. And the question, the first example of product reality, and it's showing us two different ideas, different equations. They are different, same idea, they are
So basically what we do, we write, we start, of course, we start with ideals like that. So yeah, same ideal for the whole hierarchy. The ideal, these two ideals, this ideal which is here, this ideal here, one, will be one for all equations, for all equations. Well, for the standard tools, that paper now is right. So in the case of Volterra equation, we proved it by brute force. You know that from Volterra to here, there is a neural transformation. And we actually, when we struggle with ideas, this neural help us to find the idea. But not yet, because we lose data. But this was checked, and I'm sure that the paper is finished. The statement will be was checked for new first ones, which also you take computer. No, actually, it was sometimes we do by hand. It's much useful. Like so basically, say that
answer the whole issue of ordering
No, that's not correct. I still don't have good answer to the question. Because what I say that if we can find such modeling which keep our favorite open, like hierarchy. For instance, when I say for the Terra system, I can write the full hierarchy of 3 houses. They commute, they see me. I don't need to solve it. They just
but where is this idea of the scope for I identify by using right? Tell us operators for the scope for this idea tell us right.
No, I will tell you how to scope variables. That's what we need to find. So we have some generic structure of ideal. We don't know how to do it in this ideal. We just use, this idea which probably, for instance, take something better about this. I can tell you, for instance, there is a Zen house, right? But I cannot realize. It's no work. What? No, I don't assume. I don't assume the dynamic system is below 1. I don't see that is not required for me. For me, required for just the few hours, right? Mechanical system. This question not concerned at this stage, maybe later, because later should be some representation theory for this algorithm, spectral theory, etc. But that is later. And actually, if you take even this simple question with this equation, look, if you try to solve this equation classically, that will be anything function. So one system will not be simple then function. How things work. I think we have. I try to probably that the same is no the same thing with the right. And one becomes
Partial quantization is the way.
You need Volta dissertation and Volta. Yeah, but they never write equation. They never write equation. They write something
It doesn't work yet.
it's not work yet because because this some practice which we up to now have served and this and that's why for the idea we use assumption for the idea they assume that they are kind of either well moderate or some in order of like quadratic or less. When we work with monic or spatial equation, then we use more that would be this Buchstaben. Then we use ideas that affects moderate by ways, the graded variables. And then we use grading to write the idea. And this grading helps a lot, and then you can find
Thanks a lot.